master's degree in telecommunication from the University of Bellido in Spain, with a major in communication. And he worked a couple of years at Endesa, in Madrid, in Vigo, and Endesa also.
Northern part in Spain.
And now he's a full-time professor at the Department of Computer Architecture, Electronics and Electronic Technology in the University of Cordoba. And his main activities are electronic system and electronic instrumentation.
Okay. Good afternoon. Thank you for the kind introduction. It's my pleasure to speak to you about an area of great interest to me, the application of intelligent electronic device for electric vehicle environment. In the future scenario of transport and human mobility, the optimization of electric vehicles and their infrastructure, transport and energy supply will be a key. For this reason, it's interesting to study the application of intelligent electronic device solutions for electric vehicle environment. Nowadays, the development of intelligent electronic device, IED, and communication machine to machine, end to end, is making possible that commercial applications have a relatively cheap cost. In this presentation, the development of an end-to-end based IED with an open architecture and ready to be embedded in vehicles is presented, in order to ensure proper adaptation between the electric vehicle and available infrastructure. For this, as you can see in this slide, two kinds of technologies have been proposed. First, GPRS has wireless WAN solution, which allows for communication between the vehicle and the various infrastructure that serve it. Secondly, GPS has geo-positioning standard in order to be able to plan routes based on user requirements, with respect to the vehicle battery and depending on the available charging points. In this picture, we saw the solution that is expected the IED provides to several of the electric vehicle needs. About battery monitoring, the main current limitation of electric vehicle is the autonomy of its batteries, so it's necessary to make continuous monitoring. This will allow to determine the consumption, the energy recharge needs, and distance coverage of the vehicle, helping to plan efficiently the user's route in every time. About the monitoring of vehicle subsystem, the IED prototype has been developed with enough capability for monitoring the main vehicle subsystems. Obviously, the control algorithm complexity will grow when the number of parameters to be monitored is increasing. About communication, it's necessary to use wireless communication, allowing for interaction of the system in different mobility situations with respect to infrastructure and the environment. The versatility of TCP/IP communication, along with the need for wide geographic coverage, advise the use of the GPRS technology. Road planning utilities is in focus to GPS technology, along with current tools of geo-positioning maps, and the positions of charging supply points, make possible an optimal road planning in real time and in an adaptive way. To begin with the design and architecture, start talking about the technology selected. From the different modular end-to-end technologies existing, it has been looked for a solution that incorporates the signal capture and its processing, the transfer of GPRS GSM data, and the GPS functionality in a unique device. On the basis of this criteria, the GM-X62 GPS module from the company Italic has been chosen. The internal architecture of this module is shown in this slide. This module is based on a kind of architecture that enables a solid development and it's easy to set up, thus saving time and resource. In this regard, it avoids a hardware design with GSM, GPRS and GPS separate modules and their microcontroller that would have extended the development stage. Moreover, the system's dimensions are reduced with this type of choice, facilitating in this way their future integration in an electrical vehicle. GM-X62 GPS includes a translator of Python language and a sequence of specific libraries which allows the internal programming of the module in that language by means of a virtual internal serial port. For that reason, it includes an additional non-volatile memory of 3 MB and a 1.5 MB RAM memory. In this picture, we show the power supply system. The system is filled with the battery of the vehicle and is also ready to work autonomously with a small lithium battery, in order to continue working when the vehicle battery suffers a breakdown. A DC converter adapts the battery voltage for providing the 3.8 volt constant current that the GM-X62 GPS module needs. This converter also provides a constant current to a charging control system integrated in GM-X62 GPS for backup lithium battery. In the next slide, we show the monitoring system. The prototype is ready for real-time monitoring of voltage and current supplied by the vehicle battery, in order to assess the autonomy that is left. The acquisition system uses Hall-effect sensors in a closed loop for the voltage and current measures, placed in the battery. Next, a circuit with 2 precision amplifiers is in charge of fixing the signal level to the entrance of the analog digital converter. The GM-X62 GPS module has an analog digital converter of 11 bits, being able to read a voltage level in the 0 to 2 volt interval. In view of the experimental character of the prototype, it has been considered to develop only the monitoring of the condition of the battery, leaving for coming projects the monitoring of another kind of parameters of a more specific character. However, GM-X62 GPS module has a series of input-output pins of general purpose, which can be configured both as input and output according to need. This prototype has been prepared to use the input-output pins easily. In that way, there is enough flexibility for all kinds of tests which can be required in the future. All the input-output pins of the module are connected to a CMOS stage at 2.8 volts. Therefore, the logical level they carry are the typical ones of this kind of technology. In this slide, we can see the management of geographical position and the vehicle information. The system is based on a front server, so that the IED integrated in the vehicles can send their geographic information obtained by GPS to the server. The GPS position of the vehicle is stored in this server, together with other data of telemetry and identification. The server communicates too with another GIS server in order to get cartographic information. All the information from the front server, Geographical position, monitoring data, roads, etc. can be transmitted to the user of the electric vehicle as well as to different entities of the survey infrastructures. With this system, a hypothetical entity for the traffic supervision could be aware of the status of each vehicle and act accordingly, generating different warnings or the appropriate actions. All the software used in this project is based on free software tools. Linux with GeoServer, Postgres, and Yeti for the geographic information server. Finally, it was decided to use Google Earth platform tools for the presentation of geographic information. This solution allows us to show the vehicle position as well as the alphanumeric information that can be stored. The server generates KML files with a layer to every controlled IED associated to a vehicle. The application is responsible for executing the KML file generated by the server and refreshes the data according to the area displayed on the screen. The general flow diagram of software that allows an autonomous functioning to each IED is shown in this slide. All GM-X62 GPS modules to be integrated in the system must be programmed with a sequence of operation to its proper functioning in an autonomous way. For this purpose, all the modules of the system shall have in the memory the necessary script with a programmed Python code, so that they can carry out the raw time of supervision, generation, and information delivery of the state of each vehicle. In this picture, we can see the final result of this prototype. Since the functionality of the proposed IED can be extrapolated to all types of vehicles, conventional vehicles has been used for the test. The results have confirmed a low current consumption of the prototype below 1 ampere, but that's suitable for integration into the vehicle. On the other hand, we verified the operation of main core of the geolocation system and road monitoring. One of the aspects that have been especially delicate when choosing the M2M technology and in the design of IED has been the power supply and consumption of the prototype. Our concern in that its integration would not involve an extra burden to the entire electronic consumption available to the electrical vehicle. The highest consumption of the system is given by the connection of the GM-X62 GPS module to GSM GPRS network. Since it must operate its radio frequency transmitter. In turn, consumption depends on the condition of coverage, so we have conducted tests in two scenarios. One with optimal coverage and another with limit coverage for the system to connect. This slide shows the power consumption monitoring of the prototype in these scenarios. In the plots, we see the most significant difference with regard to consumption between the two scenarios of coverage. In the situation of low coverage, we see a higher density of consumption peaks associated, as expected, to the need to force radio frequency system. By contrast, the graph corresponding to a good coverage presents a cleaner distribution with a lower peak current density. From this analysis, it should be noted that at no time was detected consumption equal or superior to 1 ampere, operating at the rated voltage of 3.8 volts. We are going with tests of system of geolocation and road supervision of prototype. In this test, the correct operation of exchange of data between the IED and the front server was verified. In this slide, it's shown a front server image with information of a series of connection with the prototype. Also, from the front server, we can get the KML file for viewing in the environment of Google Earth, access to GeoServer, and initialize the registry. To test the prototype, we are considered the following alphanumeric information: temporary mark with date and time of registration, IED identifier, data associated with the SIM card of the module, data from other entities with which the IED has communicated, IP addresses, domain names, phone numbers, etc. And finally, geographical position, longitude and latitude. About the conclusion, the use of GMX62 GPS manufactured by Italian company with integrated GPRS and GPS solution has proven to be a robust solution with an affordable price, a good value for money. From the point of view of operation of the prototype, we have found that present an average reduced consumption below 1 ampere with a supply voltage of 3.8 volts. Therefore, it is not expected to involve a significant consumption within the electric vehicle power. Finally, we have put into operation a management scheme between the IED prototype and other entities, using a front server and free software, so that the IED integrated into electric vehicles can send to the server both geographic information obtained by GPS and other data. The server stores the vehicle's GPS position and other data of telemetry and identification. That is all. Thank you very much for your attention.
Thank you. Are there any questions? I have a question. Can you please go back to the slide where the power consumption was shown, where you have the graphic of the power consumption? Can you give us a peek just at the beginning or around 10 seconds after the power up? That would be around 20 seconds. So we have always this high peak. Can you explain a little bit why the power consumption is so here and also on the optimum scenario? Also up we have this peak, and it's probably when the first communication is established, right, on the GSM.
This song is clearly view this song, and after a more stabilized song. This is the song when the transmitter contact with the network GSM and registry is identifier number 86. And after the song is when the registry has done and the module has stabilized.
And these peaks which we have, let's say 8 seconds, when data is sent over to the server, right? When you send this telemetry data and the GPS position back to the
No, I understand. No, this plot is only for the registry action. Only for the registry. But in this song, there are the modes consumption of the model. We don't need something to do this step with send information. But the maximum power consumption in this song.
So basically here, you need like 3 minutes to get a connection to the GPRS, more than get a connection to the network.
We try some connections In every case, it's sufficient 3 minutes for the test.
Okay. Thank you very much. Are there any questions? If not, thank you.